Thank you, everyone, so much for being here, and thank you, Patrick, for that introduction. Really excited to have everyone here. I also want to welcome our guests. We have representatives from the local, state, congressional levels, and the Maryland Economic Development Corporation. So we're really give you a warm welcome and glad to have you here at Goddard today. As we know, we have an extremely brilliant legacy of light here at Goddard, and we're going to go through a few of those key observatories and talk about the real wonder and excitement that they bring. We have Dr. Jennifer Wiseman. She's our senior project scientist for Hubble Space Telescope, and this is NASA's most successful mission to date, I think. It's still going strong after more than 34 years after launch. That's more than 1.6 million observations and about 21,000 peer-reviewed scientific papers, and about 1.2 million total citations in published papers. Incidentally, now the number of papers that have been published from the archive exceeds the number of papers published from original observations. It's a gift that keeps on giving. We also have Dr. Jane Rigby, the senior project scientist for James Webb Space Telescope, and this is our second science anniversary for this groundbreaking telescope. I was asked earlier, what's my favorite image from Webb? And my favorite image is the photograph that I took of the launch at the launch site in French Guiana, because that was such the start of such a fantastic journey. We also have Dr. Julie McHenry, and she is our senior project scientist for the Nancy Grace Roman Space Telescope. This year, we have now all of the parts of the telescope in our clean room here in Greenbelt, so it marks the next step of putting together this amazing observatory that will launch in just a couple of years. And we have Dr. Giada Arni. She is the interim project scientist for the Habitable Worlds Observatory. And this is the next big flagship observatory after Roman. And Goddard just opened the project office, so it's another remarkable milestone as we start our future of our legacy of light. So we have a fantastic vision. We hope that you enjoy this show. So without further ado, we're going to get started. Thank you.
T-minus 10, go for main engine start. We are go for main engine start, T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Mission Control, Houston.
Roll program. Roger, roll, Discovery.
The roll maneuver puts the vehicle in the proper launch plane.
Isn't that cool to see Hubble launch? Good afternoon. It is my honor and pleasure to celebrate with you today NASA's remarkable Hubble Space Telescope and how Hubble is a leader for the future of astrophysics. So as we talk about this legacy of light today, the theme of our event, it's fitting that we first reflect on some of the iconic imagery and scientific breakthroughs that have been enabled by Hubble. From its perch in low Earth orbit above the clouds, Hubble surprised us by revealing a universe that is active and awesome at every scale. Iconic, colorful nebulae are signposts of continuing star formation. Newly formed stars light up the surrounding gas with ionizing radiation, while winds from the stars often sculpt the surrounding star-forming dust clouds into pillars pointing back toward the stars. Hubble found that many young stars are forming with dusty circumstellar disks. We now know these as the birthplaces of planets. We've watched as old and dying stars enrich the environment for the next generation. We see our own solar system teeming with activity. We've watched weather changing on the outer planets, asteroids colliding, and even possible plumes of water vapor escaping from the under-ice ocean on Europa. I'm looking forward to Europa Clipper investigating these more closely. I think what moves me the most are Hubble's views of deep space and galaxies beyond our own Milky Way. Hubble's deep fields show that galaxies change and grow over cosmic time, that they interact with one another. Their mergers spawn bursts of star formation. Hubble first confirmed that galaxies harbor supermassive black holes at their cores, and now Hubble is discovering more of these in the early universe than ever expected. With incredible precision, Hubble has also measured the current expansion rate of the universe and refined it to the point where it now seems to conflict with predictions from standard cosmological models. So we might be headed toward new physics. Today, here, we're looking forward. Hubble is actually more scientifically powerful today in many ways than ever before. I want to share what I see as several great ways that Hubble is leading the future of astrophysics. Hubble is in good condition thanks to the series of successful servicing missions and an impressive operations team on the ground, including many right here. Experts at Goddard and the Space Telescope Science Institute address every technical challenge. They've even figured out how to precisely point Hubble using only one gyroscope, even though we have more, and how to precisely support a full suite of science instruments, including cameras and spectrographs. So it looks like Hubble will be in good shape well through this decade and beyond, and we're in good hands. I'm continually impressed by this awesome team. Hubble is in strong scientific demand. It is the only large space observatory in the coming decade with the ability to see ultraviolet light, which can only be viewed from space. This kind of energetic light is paramount for modern astrophysics. It's produced from many kinds of cosmic phenomena, from planets to star-forming galaxies. We're using this light to watch hundreds of stars. We see planetary auroras lighting up, and we study the composition of exoplanet atmospheres. We even caught an exoplanet in the process of forming as it pulls material from its surroundings. Hubble is part of a powerful team when we combine its observations with those of observatories that concentrate on different wavelengths of light, like the Webb or the future Roman space telescopes. Together, Hubble and Webb are working to generate a more complete picture of our universe. Take, for example, this spiral galaxy, with Hubble revealing hot spots of star formation all along the spiral arms, and Webb's infrared view showing the heated dust lanes. Those famous pillars of creation seem to come alive as Hubble shows the structure of the cloud, and Webb peers through the dust to see more stars and infant stars inside. Together, these observatories are looking deep into the universe to map out cosmic history as Webb detects the most distant infant galaxies, and Hubble shows us the details of star formation in similar galaxies nearby. Hubble is a powerhouse for studying phenomena that change with time. Astronomers are taking new observations and combining them with data from Hubble's incredible archive to make new discoveries that are not possible any other way. For example, we're seeing how decades of observations of Neptune show clouds coming and going in sync with the solar cycle. In concert with other missions, Hubble is transforming our view of the solar system. We're studying Jupiter's clouds and magnetic activity in sync with the Juno probe. And when the DART mission intentionally impacted an asteroid, Hubble and Webb watched the impact debris, and Hubble continues to monitor a swarm of boulders knocked away from the surface by the blast. We're better understanding how Mars lost its water using detections from the Hubble and MAVEN missions. Continuing to look forward, future astronomy missions are going to be serviceable. Our experience with 5 incredible astronaut servicing missions to Hubble is informing future mission servicing. One of the most exciting aspects of my NASA career has been to see the successful teamwork across the scientific, engineering, and human spaceflight cultures of NASA that made Hubble servicing missions so successful and inspirational. These experiences are helping NASA plan both human and robotic approaches for future missions. Hubble science teams are pioneers in including citizen scientists from the public around the world in real scientific research. For example, volunteers identified over 1,000 photobombing asteroids in over 37,000 Hubble images over 19 years. This team helped develop artificial intelligence algorithms to identify asteroids. And these techniques can be applied to future research using new approaches like machine learning and AI as we prepare for big data from missions like the Roman Space Telescope, which you'll hear about later. And beyond Roman will come the Habitable Worlds Observatory. Hubble is a primary science and technology precursor for this future observatory. Hubble views the same wavelength bands of light that habitable worlds will see, and the Hubble science in the coming decade will set the stage and build teams for the full range of astrophysics that the Habitable Worlds Observatory will address. Those teams will include young people who are inspired to enter into STEM careers because of Hubble. The mission is involving more new scientists than ever before. 1/3 of our newly accepted Hubble observing proposals are led by first-time principal investigators. And thanks to exemplary outreach, including our exemplary outreach team here, the public excitement for exploration, astronomy, and NASA is fueled by Hubble's continuing discoveries. Hubble images encourage us to reflect on what it means to be human. You know, nothing gives me more satisfaction than seeing the eyes of young people light up as they realize how science, engineering, and curiosity can unite humanity for something positive. To look up at the sky and consider the amazing universe and our place in it. I'll close with a quote from the findings presented by the last NASA senior review of the Hubble Space Telescope mission. Looking to the future of Hubble, the panel said that Hubble continues to be a scientific powerhouse, unique in breadth and depth. It is truly a great observatory. Hubble plays a key intellectual role in interrogating and challenging current scientific paradigms, driving discovery at the frontier. So I am excited about Hubble's future. And as we follow this legacy of light, let me now welcome Dr. Jane Rigby, who will tell us about the new astronomical marvel, the James Webb Space Telescope. Thank you.
Hi, everybody. Thank you for being here. The James Webb Space Telescope is the most powerful and the most in-demand telescope that the world has ever seen. Now in its 3rd year of science operations, the Webb telescope is 100 times more powerful than its predecessors. The technical performance is fabulous on every metric. It's better than requirements. It's frankly better than we dared hope. Webb's technology, namely segmented deployable space optics, lays a clear path for the future. There are papers coming out every day, a fire hose of discoveries on subjects covering a wide swath of astrophysics, from the solar system to exoplanets, star formation to supermassive black holes to the very most distant galaxies. We're doing transformative science every day, and my biggest problem right now is keeping up. Also, Webb is turning into something, a symbol to the country and to the world. Webb science is audacious and bold on a scale that only the United States can lead. Webb tackles the grand challenge of how galaxies, like our own Milky Way galaxy, formed after the Big Bang and then evolved over the 13.8 billion year history of the universe. Before Webb, we knew almost nothing about how galaxies formed in the first billion years of cosmic time. Webb has now found thousands of galaxies at those early times, transforming our understanding of the cosmic frontier. The current record holder, but it could be broken next month, is at redshift 14.3. We are seeing this galaxy as it looked when the universe was only 300 million years old. And it's now 13.8. So we're seeing back through most of cosmic time. These early galaxies are more numerous, and they are forming stars more rapidly than we expected. Many of these galaxies have rapidly growing, already supermassive black holes in their centers, again, earlier than we expected. We're measuring what these galaxies are made of. We are charting how the stars created the elements, the carbon, the oxygen, the nitrogen, that make up our bodies and are necessary for life on Earth. Webb is showing us how these small, early galaxies evolved over cosmic time into galaxies like our home, the Milky Way. Much closer to home, Webb is studying galaxies like our own Milky Way, often working in tandem with Hubble. Webb studies exoplanets, which are planets orbiting other stars. Webb is telling us what the atmospheres of these exoplanets are like, measuring many molecules like water, methane, ammonia, carbon dioxide, carbon monoxide, enough to determine the chemistry of these exotic worlds. And when I say exotic, I mean exotic. Many of these planets that Webb is studying are like nothing in our own solar system. We're studying Jupiters that orbit their star once a day. We've studied a rocky planet with a temperature of 3,000 degrees that's covered in lava. For small rocky planets, Webb is delivering fabulous precision, such that we're often limited by what's going on the planet, clouds, host star activity, rather than anything going on in our very stable telescope. Looking at TRAPPIST-1, which is the closest exoplanet system that might be habitable, Webb has shown that there are not thick atmospheres on planets B and C, and we're continuing to study the other planets. And that's just the early science. Webb is now building on those initial discoveries, digging deeper, getting more diagnostics. We've really following up on those early surprises and hitting our stride. Now, I'm asking, and I bet you're asking, do any of those exoplanets host life? I want to know that too. Are we alone or not? Webb can search for atmospheres on Earth-sized worlds. But is there life? As you'll hear from Dr. Arney, that requires a bold new telescope. I want to take a moment to celebrate the team. Webb's success is due to the hard work of about 20,000 people from 14 countries, industry, academia, 3 space agencies, all coming together to do something audacious. Some of those 20,000 are probably in this room, so you know who you are. Thank you. Scientists from about 57 countries and counting have proposed observations on the Webb telescope. And scientists in almost every state are analyzing Webb data. And Nebraska, I'm looking at you. We'll get to all 50. Webb was an audacious thing to build, and it works exactly as it was designed to do. Its task was to unfold a telescope much bigger than its rocket, to unfold and tension a sunshield that's the size of a tennis court, and then make all 18 primary mirror segments work together as perfectly as physics allows. All done in the dark, alone, headed out 1 million miles away from the Earth. And it all worked. That success is no accident. It required exceptional engineering. At every step, from the early concept to a methodically thought out design, and now a highly productive observatory. And now that Webb works, it lays the technical path for what comes next. Webb demonstrated that we can build and deploy telescopes that are bigger than the rockets that carry them to space. Webb demonstrates US leadership in large space optics. Every few days, Webb senses the position of each mirror to a few billionths of a meter so that we can move the mirrors into perfect alignment. This exacting technology, called wavefront sensing of deployed segmented space optics, was developed for Webb, is key to our technical success, and is absolutely pathfinding for the Habitable Worlds Observatory. Webb also couldn't be fully tested on the ground. Computer models anchored to real-world tests perfectly predicted how the telescope behaves in space. So this engineering experience from Webb means that the Habitable Worlds Observatory, out of the gate, is much further along than was Webb at a similar stage. So Webb is a revolutionary scientific instrument, and it's a triumph of engineering. But as I give talks to the public and I give media interviews, I've come to realize that it's something else. It's become a symbol. Webb demonstrates US leadership in STEM. It demonstrates the power of international cooperation. It's a kind of soft power ambassador, a reason that the United States and its partner countries are admired around the world. When we launched Webb, everyone was rooting for it. So Webb became a symbol of what we can accomplish when we work together, a symbol of striving collectively for a greater purpose. And also, Webb images speak to people. They remind us that we're connected to the universe, that we're part of a bigger, transcendent story, that we really are literally made of stardust, and that each of us belongs to the universe. So I've come to realize this. Maybe it's cheesy, but I think it's true that Webb's exploration of the universe is good for the soul of our country. History will remember these telescopes and what they've learned long after we're gone. So looking ahead, the best science with Webb is still ahead of us. We are just now getting to the good stuff. And also, I can't wait for when Webb will be working in tandem with the Roman Space Telescope. Webb's technologies of deployable space optics and wavefront sensing are the building blocks needed for the Habitable Worlds Observatory. So in closing, working together, we built something incredibly hard to build and so powerful. Webb works beautifully. The science is pouring down like a waterfall. Webb shows us the universe that's been out there all along, waiting for us to open our eyes and see. Next, Dr. Julie McHenry will describe the next NASA astrophysics flagship, Roman.
After more than 30 years of observations, Hubble continues to revolutionize our understanding of the universe. But what about what it hasn't yet seen? Most of the sky remains to be explored. And this is where the Nancy Grace Roman Space Telescope comes in. Using the same sensitivity and performance we've come to expect from Hubble, Roman will have a much larger field of view, allowing us to see more of the sky at once. Where Webb goes deep, Roman goes big. It starts with our field of view. At any instant, Roman will see 200 times the amount of sky that Hubble can see. But it's more than that. Roman will move and stop and be ready to take the next image very quickly, so it can survey the sky more than 1,000 times faster than Hubble. To put this into context, a survey that would take Roman 1 month would take a century with Hubble. So Roman doesn't do Hubble science faster. It can address entirely new, ambitious science questions. This leads to extraordinary capabilities. That 1 month of Roman observations could survey the Milky Way, resulting in the detection of over half the stars in our galaxy. Those over 50 billion stars would represent a catalogue of astronomical objects much larger than any in existence today, with just 1 month of Roman observations. Periodically, Roman will turn its sights towards the center of our galaxy and monitor 200 million stars in a small patch of sky every 15 minutes. But it won't only image millions of stars, it'll discover tens of thousands of new exoplanets. To date, we found around 5,000 planets beyond our solar system. With Roman, we'll find up to 40 times more. Think of this as the largest census we've ever done of other planets in our galaxy. This will not only provide critical information into how planets form, but will also reveal more about the different types of planets that exist around different stars. Such information will not only help us understand the nature of other planets, but also of our own solar system. We'll be able to delve deeper into the unknown. The physical nature of dark matter and dark energy, which drive the evolution and future of our own universe, remain outstanding grand challenges in both physics and astronomy. Addressing these was a prime motivation for Roman. We'll address this in 3 different ways. Our universe is a very dynamic place that puts on spectacular cosmic displays every second. The problem is that these events happen very quickly and often elude our telescopes. With Roman's panoramic vision, we'll not only catch these events, but see many at once. We'll see tens of thousands of supernovae and use these as markers to track the expansion of our universe. We'll map huge swaths of the sky and find billions of galaxies. We'll measure the shapes of these galaxies and use this to uncover the distribution of dark matter in our universe. And third, by precisely measuring the position and distance of galaxies, we'll be able to create a 3D map of the universe and watch how it changes on large scales over time. These 3 investigations combined will enable us to study how the structures in our universe, the stars, the galaxies, and clusters of galaxies, grew and evolved. They'll also allow us to measure how our universe has expanded over time. These are the keys that will allow us to unlock the fundamental nature of dark energy and dark matter and the fabric of the universe itself. These studies are even more exciting now. As Dr. Wiseman mentioned, we are seeing hints that our standard model of the universe is incorrect. Roman will be able to confirm this and provide the data needed to explore the new phenomenon. So it's really tremendously exciting. We're likely to go beyond current models and get to explore entirely new phenomenon for the first time. We happen to be the right mission with the right capabilities at the right time. What makes me most excited about Roman is the discovery potential. With 2 billion galaxies, we'll have 2,000 objects that are 1 in a million. We'll be exploring patches of sky over a function of time with exquisite sensitivity. We'll find new things that go bump in the night. I very much hope, and in fact expect, that the most exciting science from Roman will be a surprise. Something we couldn't predict, that will set the stage for the next deeper set of questions about our universe for future missions to address. Roman is being built right now. Over the past few years, we've been busy building and testing Roman hardware. We've installed an astonishing 45 miles of cables, the observatory's nervous system, into the spacecraft structure. We've integrated other critical elements, including the propulsion tanks. We've also installed a deployable high-gain antenna, which will support data transmission rates up to 500 megabits per second. This is much faster than my home internet. And Roman needs to do this wirely from 1 million miles away. We've completed the outer parts of the observatory, including the solar panels and sun shields. We've finished and tested the outer barrel assembly that will ultimately surround the telescope. The wide field instrument, our primary instrument, has now concluded testing and is awaiting further integration at Goddard. This is the part of the observatory that provides the huge field of view that drives Roman's revolutionary science reach. This instrument is a symbol of our critical partnerships. Engineers from Goddard and BAE Systems have been working side by side to make Roman's wide field of view the best that it can be. BAE enhanced the Goddard design for the instrument, resulting in better sensitivity and more flexible observing options. We'll have a better observatory as a result. Our telescope, built by L3 Harris, has arrived at Goddard and has been integrated into the instrument carrier last month. You should come to the clean room and have a look. It's all there. This coming year will be very exciting as we watch the observatory take shape. We'll assemble the components into the complete Roman observatory and carefully test everything. All the remaining assembly and test will be happening at Goddard, and we'll be taking advantage of all the large integration and test facilities here. Roman development is proceeding on budget and on schedule, and we're looking forward to getting it to the finish line. I really can't start to express how exciting it is to see everything coming together. Every day, we're learning more about just how great this observatory is going to perform. Each NASA astrophysics mission builds on the technology successes of the past. A great example of this is the sensors at the heart of Hubble, Webb, and Roman that produce the great images of the universe we've all come to love. They represent a continuous line of development and innovation, starting in the 90s with the development of the 1K detector in Hubble's WIF-C3, further developed and improved for the 2K detectors in Webb's NIRCam, and finally culminating in the 4K sensors in Roman. Each generation of sensor represented a big leap in performance. With Roman, we start a whole new path of technology development with the Roman coronagraph, which was designed and built at JPL. A coronagraph is a type of instrument that can zero out the light of a bright star so that we can directly image planets and other faint objects beside it. For the Roman coronagraph, I think of this as doing magic with physics. We're taking advantage of the wave properties of light to cancel out the light from the star. To do this magic, we need to have an optical system that can adjust itself to maintain sufficient precision. This will be the first time that this kind of active optics has been used in space and will set us on a new path for future observatories to do extraordinary new things. Our namesake, Nancy Grace Roman, NASA's first chief astronomer, would be excited not just by how far we have come, but by where we are going. She is widely known as the mother of Hubble. Less well known is that in 1959, she was one of the first people to suggest using a space-based observatory to look at planets around other stars. Dr. Roman felt that such an observatory would be too big and too difficult to be feasible in orbit. But with developments from Hubble, Webb, and soon Roman, this is now within reach. And the next speaker, Dr. Giada Arni, will describe what the next leap in space-based astrophysics will bring.
Good afternoon, everyone. Take a breath with me. Breathe in, breathe out. All of us in this room are breathing oxygen, and that oxygen is a way that our planet's biosphere has been saying hello to the rest of our universe for billions of years. Virtually all of the oxygen that we're breathing right now is a byproduct of oxygenic photosynthesis, our biosphere's dominant metabolism. When photosynthetic microbes evolved billions of years ago, the oxygen that accumulated over time could be detected across the light years. And all you'd need is a powerful telescope and a little knowledge about photochemistry to realize that Earth's atmosphere is too weird to explain without life. We call remotely observable signs of life biosignatures. Oxygen is not the only one. Others include ozone, methane, nitrous oxide, and more. The Habitable Worlds Observatory, or HWO, will be the first observatory designed specifically to address one of the most important questions in the history of humanity. Are we alone? Achieving this will require some breathtaking technological advancements. HWO will, for the first time, study the atmospheres of Earth-like planets around stars like our Sun. Think of them as our cosmic cousins. To do this, we want to observe the planets directly in reflected light. This will be challenging. An Earth-like planet is 10 billion times dimmer than a star like our Sun. It's hard to visualize what this means. People will often use the analogy of seeing a firefly next to a lighthouse, but that's not a perfect analogy. The firefly is too bright, and the lighthouse is too dim. But you get the idea. This is going to be very challenging. To see the planets, we need to block out the starlight with powerful new technologies. HWO will build on technological advancements already underway. As you heard from Dr. McHenry, the Roman Space Telescope will include a complex coronagraph to block out the starlight and study exoplanets. HWO will include an even more powerful coronagraph, able to see planets the size of Earth. That complex instrument must be paired with the most ambitious telescope that NASA has ever built. We will draw from the lessons and technologies of previous observatories, including Webb's amazing segmented telescope, which is performing beyond expectations, as you heard from Dr. Rigby. Goddard's ultra-stable technology development will take us beyond Webb to the image quality that we need in the search for life. We'll start by looking for planets in their star's habitable zones. The habitable zone is the region around a star where you can have liquid water on a planet's surface. But not all planets in the habitable zone will actually be habitable. For example, if you are looking for a chocolate chip cookie, a bakery is a good place to start. But not every cookie in the bakery will be the type you're searching for. You'd need to examine each one to determine which ones are actually chocolate chip. Likewise, we will need to carefully measure the light from each planet in the habitable zone to search for the spectral fingerprints of water and determine which planets might actually be habitable. But telling whether a planet is habitable is different from determining whether a planet is inhabited. And that's where the search for biosignatures comes in. We'll look for those important gases like oxygen, methane, and ozone. Of course, we also want to avoid being fooled by false positives. Those are non-living planets that look alive. That's like thinking something is a chocolate chip cookie, but then biting into it and discovering that it's an oatmeal raisin cookie. So, to rule out false positives, we will need to carefully study all biosignatures in the context of their environments, and HWO will be designed to do this. With a telescope like HWO, we may know the answer to the question, are we alone, within our lifetimes? This would be one of the most important discoveries, not just in the history of science, but in human history. But it's important to emphasize that like NASA's other great observatories, HWO will be capable of game-changing discoveries across a broad range of science areas. It will be a full astrophysical observatory studying the entire universe. For every possible Earth-like planet discovered, HWO will discover 10 times as many other kinds of planets. Those hundreds of other worlds will help us to understand our own solar system in a broader cosmic context. Now, speaking of our solar system, I like to call these nearby worlds the exoplanets in our backyard, and we will be able to see them in incredible detail and high definition with HWO. For example, this beautiful image of Jupiter was taken by the Juno spacecraft, and incredibly, when Jupiter is at its closest approach to Earth, we will be able to see almost this level of detail on Jupiter with HWO. Hubble, Webb, and soon Roman have been and will be providing literally astronomical leaps across astrophysics. HWO will too, reaching unprecedentedly faint objects with unmatched clarity. Galaxies are among the most beautiful objects in our universe. They are complex arrangements of stars, gas, dust, dark matter, and more. We know that galaxies grow through the mergers of smaller galaxies, but we still have questions about the details that drive them to have different morphologies and star formation histories. With HWO's high-resolution imager, we will be able to further our studies of galaxy formation by resolving small, faint galaxies in the very distant universe, including galaxies smaller and fainter than the ones we have been able to study before. These galaxies, which are the building blocks of galaxies like our own, are about as faint as the Earth-like planets we're searching for around nearby stars. Studying them will help us to help better understand how our own Milky Way came to be. And as we think about searching for signs of life beyond Earth, we should remember that the tree of life is rooted in the stars. The elements that make up our bodies were forged in stars billions of years ago. HWO will help us to trace these cycles of matter across the universe. If galaxies are the factories of stars and planets, this hot gas flowing between galaxies is their fuel tank, waste dump, and recycling center. Most of this cycling of hot, tenuous matter is currently unobserved, but HWO will map these streams with unprecedented sensitivity in the ultraviolet. As you heard from Dr. Wiseman, a major part of Hubble's unique legacy comes from access to observations in the ultraviolet, and this will be a significant part of HWO's science story as well. We will also echo Hubble's legacy as a multi-generation observatory, lasting for decades, thanks to in-space servicing. HWO will continue and expand the great legacy of light of NASA's flagship observatories, such as Hubble, Webb, and Roman. We don't yet know exactly what HWO will look like, but we can safely say that this project will be a momentous undertaking. It's going to take a village, including Goddard, other NASA centers, industry partners, academia, international partners, and the broader community. This pale blue dot image of Earth was taken by NASA's Voyager 1 spacecraft when it was almost 4 billion miles away from the sun. What might it mean to see another Earth? Another pale, point-like vision calling to us with its light from deep space? Is Earth alone in the universe? The Habitable Worlds Observatory will be capable of addressing some of the biggest questions we have today, and questions that we can't yet think to ask. Now let's close the show with a final glimpse of what's on the horizon, the legacy of what we're building, what we're discovering, and the incredible journey ahead. Let's roll the video.
We have always looked to the sky in wonder. Questioning the universe's story and our place in it. In the vastness of space, are we alone? Each generation of telescope and technology has brought us closer to the answer. Human determination has taken us farther than we could have imagined. This legacy leads to our next chapter. And the answers that lie in the stars. Waiting for us to find them.